So this is a problem that involves coming up with a Langmuir-Hinshelwood mechanism and then evaluating whether that mechanism can explain some kinetic data in the second part of the problem. In this case, we're dealing with the hydrogenation of ethylene to ethane conducted over a nickel catalyst, where the mechanism is proposed to exist of just a few simple steps, shown here, which involves the adsorption of ethylene onto a surface site in reaction 1 to form adsorbed ethylene in a reversible step, the dissociative adsorption of hydrogen onto two surface sites to form two hydrogen atoms, and then adsorbed ethylene reacting with two adsorbed hydrogen atoms to produce ethane directly in the gas phase, which is pretty typical because ethane is very weakly adsorbed, which frees up those three surface sites to participate in another reaction in the cycle. All right, and we're given in the problem statement in this case that the rate determining step is step 3, and so the other steps will be assumed to be equilibrated. And we'll describe those in terms of adsorption equilibrium constants. All right, so let's look at how to set this up in a mathematical Langmuir-Hinshelwood format, which is what A asks us to do, and it asks us to do that in terms of equilibrium constants for the reactions and the forward reaction rate constant, as well as the total concentration of surface sites, CT, available for reaction. All right, so if we want to set this up, we need to start writing our equilibrium expressions. And so the first one for the adsorption of C2H4 basically says that the equilibrium constant for process 1 for adsorption is equal to the concentration of the products of that reaction, which is adsorbed ethylene, over the concentration of the reactants, which are vacant surface sites, and the concentration, or normally we express this in terms of the partial pressure of C2H4. All right, so we can define that equilibrium relationship because that adsorption step is equilibrated, and it's going to be more convenient to express that this way, that C2H4 adsorbed is equal to K for step 1 times P C2H4 times the concentration of vacant surface sites. All right, very similarly, if we look at step 2, the dissociative adsorption of hydrogen, we can write that in terms, I'll just go ahead and skip the first part of this, and we can write that in terms of the concentration of sites on the surface, of sites containing hydrogen on the surface, squared is equal to K2 PH2 star squared. All right, and in this case, we carry along the squares because the stoichiometry dictates it that we have two surface sites participating in the reaction and two hydrogen atoms participating in the reaction. And I initially skipped this, but maybe I should go ahead and show it. That means that products over reactants will be H star squared, the concentration of hydrogen squared, our product, over the concentration of star squared, one of our reactants, and then it's first order in hydrogen concentration or pressure, so we don't square that term. All right, so these are two equations that are going to be useful to us. And another way of writing this equation, I'll maybe call that 2a, is taking the square root of both sides. We're going to find that to be useful. So it'll give us H2, or H star, is equal to the square root of K2 PH2 times the concentration of vacant surface sites. Okay, so those are our equilibrated steps. And then the other element of a Langmuir-Hinshelwood expression is a site balance, where the total number of sites, the concentration of total sites, is equal to the sum of all the different types of sites you have on your surface. So one of those types is vacant sites. We also have sites that contain ethylene, and we also have sites that contain hydrogen. And all of those add up to some total concentration of sites that must be conserved during the reaction. In a catalytic reaction, we don't generate or remove sites in the simplest approximation. All right, we can substitute in for this, and I'm going to go ahead and factor out the concentration of sites. All right, so we have 1, if we factor that out here. All right, C2H4 star from equation 1 is equal to K1 times P2CH4 plus this concentration of vacant sites, which we've factored out through this term. All right, and so that's equal to 1 plus K1 PC2H4 plus, all right, H star we see is equal to the square root of K2 PH2 times the concentration of vacant sites, which we've again factored out. So we just get the square root of K2 pH2 here. All right, so that's the total concentration of sites in terms of the concentration of vacant sites. So we've eliminated some unknowns from this expression, which will be useful for us. All right, and then finally, we can write this rate of reaction. We need to express this as a rate, as what the problem asks us to do. Right, and that's equal to the rate of reaction 3, which is shown here. And we're given that this is a reversible reaction, so we need to include both the rate of the forward and the reverse process. So let's go ahead and do that below. All right, so it's equal to K3, the rate constant for the forward process, times the concentration of ethylene adsorbed on the surface, times the concentration of hydrogen adsorbed on the surface, squared, because 2 hydrogen atoms participate in that reaction. And we assume an elementary reaction in this Langmuir-Hinshelwood mechanism, minus the partial pressure of ethylene, since it's the concentration of the product that we need to take into account for the reverse reaction, times the concentration of vacant sites cubed. And we divide that by K3. All right, again, because there are 3 vacant sites, if we go back up here, that participate in the reverse reaction, 3 vacant sites plus ethane. Okay, once again, what we would like to do is be able to express all of this in terms of rate constants, equilibrium constants, and the concentration of total sites, which is a quantity that's conserved, because it's very difficult to actually measure the concentration of vacant sites, hydrogen-containing sites, and ethylene-containing sites. All right, and so in order to do that, the strategy that we'll use is to substitute everything in so that we get only the concentration of vacant sites in here. We have enough relationships to do that. So let's see how this works. All right, so this rate is then equal to K3. For C2H4 star, we have a relation up here, equation 1, that relates that to star, to the vacant sites. All right, we have an expression for H star squared. All right, we have this part of our expression. And make sure that this is a capital K3. Okay, so if we collect terms, this becomes a vacant sites cubed, both in this part of the expression and here. And we can factor that out, a vacant sites cubed out here. And we have in expression, I'll call it 3 here, the concentration of vacant sites. We can express that in terms of only constants and pressures, things that we can measure and fit, right? And the concentration of total sites, which is conserved. And so we'll combine equation 3 with equation 4, and I'll re-express that. We get that the rate is equal to the total concentration of sites cubed times K3. If we collect terms, we get these K1, K2, pressure of C2H4, pressure of hydrogen, minus the pressure of C2H6 over K3. And then we get the typical Langmuir-Hinshelwood denominator term, which is 1, which stands in for the concentration, the relative proportion of vacant sites. The more important the 1 is compared to the other terms, plus K1 times the pressure of C2H4, which relative to the other terms is proportional to the number of sites covered with ethylene, plus square root of K2, pressure of hydrogen. And then this entire term is taken to the third power, right, which originates from the third power right here. All right, and so we see now we've done what the problem statement asked, and we've expressed everything in terms of equilibrium adsorption constants, which we can fit to a model, as well as a rate constant, which we can also just fit if we vary the pressures of hydrogen and ethylene and measure the rate, and the total concentration of sites, which often is lumped in with K3 because it should be fixed during the reaction as long as you don't have substantial catalytic deactivation. And now if we turn to part B of this problem, it shows you some experimental data in which the partial pressure of hydrogen has been varied at fixed partial pressure of the other reactant, ethylene, and the outlet flow rate of ethane has been measured in a differential kind of reactor. All right, and so what we see, you can go through a more rigorous process here, but we'll just look at this very simply because the trends are pretty simple. If we quadruple the inlet flow rate or the inlet concentration of hydrogen from 10 to 40 and then from 40 to 60, so each time we're quadrupling that, then we only double the outlet, we only double the productivity, so we only double the outlet flow rate of ethane, of our product of this reaction. So that means that here the rate is proportional to the pressure of hydrogen to the 1/2 power. Right, because when you quadruple the amount of hydrogen, you only double the rate. So that's a square root dependence. Right, now let's see how this compares to our expression. We furthermore note that it is known that the hydrogen coverage on the surface is very low under these conditions. Right, and that happens to be true for this kind of catalyst. Okay, we know that the coverage of hydrogen is very low, and so that means that this term, which describes the coverage of hydrogen, is very low compared to these two terms, the 1 plus K1 Pc2H4. And so we can assume that this is negligible and goes to 0. We furthermore can assume, although we don't have to with this problem, it makes it simpler, that because we're not feeding any ethane and this is a differential reactor so the conversion is low, that this term goes to 0. So there's very little ethane in our reactor, and we can assume that this goes to 0, which happens to be also a very good assumption for this particular reaction. And so therefore, what our model predicts is that the reaction should be first order in hydrogen. Notice we get this first order dependence in our model. But what the experimental data told us, remember, is that it's actually half order. And so this model that we've proposed is not consistent with the experimental data. And we needed to actually go and propose another model that could be consistent with the experimental data. And we won't include this in the screencast. One productive thing that we might think about doing, and which will actually lead to a model that's consistent with the data, is to, instead of assuming that both hydrogens add at once, we could assume a sequential process where first one hydrogen added in order to make ethyl in the rate determining step, and then we had a second process where the next hydrogen was added in a fast step that we assume does not contribute to the rate. And if we use this, we'll see that we can get an expression that is consistent with the experimental data here. And makes sense anyway, since, as we've talked about previously in class, these kind of three body collisions where two hydrogen atoms simultaneously collide with an ethylene molecule are unlikely, and that's true both on surfaces and in three-dimensional space.